Yeah, thank you very much, Turaj, for the kind words. Thanks also, Christian, for inviting me to this great place. It's really a pleasure to be here and talk about, as I called it, a content creator's perspective. I now work for Disney Research, and we are, well, the world's largest entertainment company. So we have a very strong interest in quality of experience. So everything that you guys do is of highest interest for us as well. I will not talk about coding almost at all, but it will be more really on content creation and related aspects of that. But first of all, well, what does it mean? So research for an entertainment company, why that? What is that? No? So IT companies have research labs, but why does Disney establish, why do we have these research labs now, one in Zurich and one in Pittsburgh? Because if you think of Disney, the first thing that people have in their mind is animated movies. So from Mickey Mouse, Donald Duck to Beauty and the Beast, Tangled, and all the Pixar movies that we have today. And that's all true. So we are doing animated movies. But as I said, Disney is the world's largest entertainment company. And it brings together a variety of very diverse business units, but they are all coupled by the common umbrella that they create content, that they create stories and characters, and they do entertainment. So they are the feature animation studios. Also Pixar is doing animated movies, but there's also live action studios, Pirates of the Caribbean. We acquired Marvel, so also the Iron Man, Avengers franchise is now part of Disney. Also Lucasfilm was acquired, so watch out for the next Star Wars movie. It will also be a Disney production. So that's all film with all the home entertainment, DVD sales that belong to that. But there's also a lot of television. We have ABC in our family, ESPN, the world's largest sports network. All of those form also the Disney channels, what we call the media networks business units. Then there is the parks and resorts, Disneyland, Disney parks around the world, cruise ships, hotel chains, all of that belongs to that. But then there's also consumer products, computer games, comic books, and all of that together. And you see, by design, all of this is coupled through a lot of synergies. No? So if there is a new Pixar movie, there will be the toys in the shops, there will be a computer game, there will be web pages, and all of that shall go together and create a value for our company. And technological innovation already has a very long tradition also in Disney. So what you see here is a patent from 1931, and it's Walt Disney himself is on here. And it was about synchronizing sound with video, something that didn't exist at that time. And he had this idea for a new creative product, so let's do a movie with sound. And so he got together with some tech guys and invented this thing that he needed for his idea. Later, he had this idea of creating the first evening-filling 90 minutes animated movie, something that didn't exist so far because it was just impossible to draw all these 25 images per second to create 90 minutes of a movie. So they came up with an invention, the multiplane machine, where you could, this is different layers of glass, and you would, for instance, draw the background, which wouldn't change over time, on one of the layers and the moving objects on others on it. And then there is a camera here that would then take a picture through these layers of glass. No? So it's a kind of, the invention of video compositing is basically made here. And it enabled a new creative and a new business concept, and it involved also technology. No? But also in recent years, this spirit of art and technology is still living. A good example is so this is John Lasseter. He was the creative mastermind of the Pixar animation studios and director of many of their movies, Toy Story, Cars, and others. And he is also a tech guy. So he's a geek and nerdy, but at the same time, he's an animator. So he was early interested in computer graphics movies. No? And he got together with this guy who is Ed Catmull, the co-founder of Pixar, and he is a computer scientist. So he has a PhD in computer science. He was making big contributions to the SIGGRAPH community in his early years. And he had this vision to create the first computer-generated animated movie. So these guys, they came together, art and technology, And they were the driving forces behind the Pixar animation studios, who were really, yeah, as you know, very successful. And yeah, Disney acquired Pixar, and they also acquired a bit this spirit of art and technology. Although our product is always a creative one, but technology is needed to create it. And that was also the spirit why Disney Research was established as a corporate level research lab that should connect to all of these business units that you saw on these other slides and solve technological questions that they will have for their, to create their business, their creative content. So we are covering various research fields in kind of groups where senior researchers work together with postdocs and PhD students, pretty much like in a university setting. So one of our groups in Zurich is the Advanced Video Technology team, where I do all sorts of video processing from capture to display, as I will tell you a bit more in a minute. Yes, I also said quality is, of course, of utmost importance for Disney, and in fact, Disney wants to define as a quality label. No? So if you buy a Disney Blu-ray, you will see something like this, Blu-ray 3D, and it has the Disney D inside there, so it shall guarantee kind of a quality standard for this three-dimensional movie that you buy on this Blu-ray that you should trust because you trust the Disney brand. As it is the world's largest entertainment company, family entertainment is the main focus, and people trust us. No? So when they come to the parks, they feel like they are in the most secure place in the world. And the brand is also one of the most valuable. And as I said, it stands for quality and trust. No? So quality of experience, consumer satisfaction is of highest importance in all these things. And yeah, we do stories, we create characters. These products have an emotional impact on our customers and technology. So what we are doing is always serving these goals of creating story character, creating customer satisfaction, and with that, this trust in our brand. Okay, so that was a little bit of a marketing, and now, as I titled that, I have a long experience in stereo 3D and beyond, and also my group, we were working a lot on related technologies. I don't want to bore you too much with that, but we should understand that what the perception of 3D means. No? So perception of three-dimensional world. So our natural perception, our brain brings together a lot of different cues that it samples of the 3D environment that all together are processed in a cognitive way to create this 3D perception of the real world. So here's a list of them, and most of them are in fact monoscopic, so they don't require actually to have two eyes. There are only a few convergence and disparity that require the two eyes. Just a few examples. So if you look at this image, size consistency tells you already something about the depth structure of the scene. You know that these cars it's the same car, so that one must be a few meters behind the other. Also, if you look at that, you know, a fish, a hand, and the relation to a man, you almost feel like how far he is standing behind the fish. So just like from size consistency, we get an understanding of depth. Also, a very strong cue is overlapping, interposition. So if something occludes something else, it is in front of it. And that's in fact a clue. This is the one clue that is most important for very distant object. And if you look at something very far in a distance and you want to see what is in front of the other, you will unconsciously, you will be moving and trying to create this effect of motion parallax, because that will tell you the order also in a Z space. That's a motion parallax interposition. It can be ambiguous. So here it is clear. This is not so clear if this is a Pac-Man or a circle. Also perspective tells you a lot. So perspective and size. So actually these two in this image, they have the same size, but you have a completely different perception about just from this very strong cue of perspective that is given here. Now also here, these two monsters, if you measure them, It's exactly the same size, but just the perspective tells you the one is giant and the other one is small. No? Yeah, also these two lines are of the same length. Also these two lines are of the same length. So then another cue for very distant things is that we have learned that things that are very far away, they get hazy, they get this bluish structure. So we know that something that looks like this must be very, very far away. And that's also, for instance, what painters know. So when they paint landscape in the Renaissance, you know, they give you a sense of very far away depth in the Mona Lisa, for instance, by using that as a stylistic means. No? Also light gives you, and these are coming out. Probably this one you are not so sure what happens because you have an understanding of how light falls into a scene. And here also, I don't know if you see much of this. If I turn the image around, it's really the same image. Just by turning, the shading now makes sense. Light comes from above, the shadows, and you see something in this image. Same here. But then there is something that we call accommodation. So if we focus onto something, we have sharpness on that point that we focus at, and everything that is behind is blurred. So we can have an understanding of close and behind and from where we have the sharpness and where we have blur in relation to that. So that's also something that photographers and cinematographers use all the time when they do depth of focus. They direct your attention by blurring the background and having, for instance, the face of the main actor that you should look at in focus. Accommodation. And finally, the one that we actually need the two eyes for is the convergence. So if you converge on something, you have a very direct understanding of how far this is away. So also if I look at this window there, my eyes converge on a certain distance, and I have a very direct measure of how many meters this is away. But also this convergence cue also is only works reliable on a pretty short distance, but as I said, in the longer distances, then rather the motion parallax takes over. And also with the convergence, we have the cue that if you focus on something, you have the convergence here, and objects that are in some relations to it, they create what we call a disparity on your retina, and by fusing these disparities, you have a notion of how relatively these things in a certain range around your converging point are to that one. Now, so all of these cues together in nature form our perception of the depth cue. And in fact, when you close your eyes and you don't look at something and then you open them, you start scattering. So you take samples of the scene, and your cognition builds up in a cognitive process this perception of your environment. So then if you look in a different direction, you also take samples, you scatter, you measure distances, and you map this into your mental model of the 3D world, and then you have it. So it also takes a little bit of time to create a 3D impression. But of course, let me jump to this one. No, the principle that you can, just rather jump to this one. So this is the principle that you can create the illusion of the 3D perception by projecting two different images into the eyes of the viewer is known already almost as old as photography itself. So if you look at this, is the oldest 3D display described, and you have two mirrors here, and if you go very close to this with your eyes, your left eye will see this image, if you have a photograph here, and your right eye will see this image. So now if these two images are taken or are created very carefully such that they correspond to something that was maybe captured by two cameras, and you project that into the user's eyes, your brain will automatically create the illusion of a 3D perception. And I say this very consciously that this is really an illusion. So it's a brute force fake of the human visual system. This is nothing natural. So you can imagine that if these two images are not created very carefully, if they, for instance, have some slight vertical misalignment, if they are maybe even rotated, if the color of the two is not balanced, or if the white is not balanced, all of these things will create an unnatural perception. So your brain will have to fight these counter arguing cues to create this illusion. But nevertheless, people have presented various 3D display systems already from very early on. There were ups and downs. 3D was coming and going. And, well, today, many people think that it's now here to stay. So what are the reasons that it, for instance, went away when we had anaglyph in the 20s? Well, there was this new technology. People said, wow, wanted to see these movies. There was a hype. But very soon it all went away. No? Well, the main reason was that the quality of experience didn't work. No? So these types of glasses cannot have a natural color reproduction. So it just will not look right. No? Or if you think of, at that time, they had these film projectors rolling. There were 2 projectors rolling independently for each eye. And you know this is shaking. So this will present you an image that is constantly shaking, and that creates exactly these bad effects of bad stereoscopic projection, and over 90 minutes you would just get a headache and get motion sick of that. So the technology was not mature enough, the content creation was not understood well enough, and you can summarize quality of experience didn't work in that time. So then nowadays many people think, well, now we have stereo 3D established in cinema, we see good movies, also there are bad movies, but many good movies are coming. It has also reached the mobile user. There are 3D TV channels. You can buy 3D Blu-rays. You can buy 3D cameras for the home. And also the technology is available for the whole chain, and it's mature enough. No? So we have digital projection. We have good 3D systems, like I believe we will see some of that later here. So many of the technical imperfections are resolved, and also the content creation side is maybe understood well enough. That's what people hope, at least. No? But you may also say that this is not really, 3D didn't really take off yet. And for instance, ESPN just switched off, so our sports television switched off the 3D channel. They had it running for 2 years, but it never really got the customer acceptance and satisfaction, and they invested a lot of money in building all this up, but finally now they decided to switch it off. So 3D TV doesn't really work. You can, 3D Blu-ray is still there, 3D cinema is there, Sky in the UK and other television stations will continue with 3D, but ESPN decided, well, it doesn't make sense for us at this point. And one reason that I hear is also that, yeah, this side-by-side format of reducing the resolution of each eye just to pack it into a normal video channel is just not meeting the quality of experience that people expect. No? Yeah, we saw this, but now let's assume we have these 2 images created perfectly fine. We have taken all care about having as natural as possible representations here. Still, there will be an inherent problem with all stereoscopic 3D presentations. And this is called the so-called accommodation convergence conflict. So if you look at the screen, the maximum sharpness is always on the screen. So your eyes will try to focus onto the screen. At the same time, if something is floating in the air in front of it, your eyes will converge onto that position. So there will be a decoupling of the accommodation and the divergence. So the accommodations will still try to be on screen, and the divergence will be wherever you converge to. So in nature, if I converge on something, also the accommodation is all of that. So these 2 cues are always coupled. In every stereoscopic 3D or also orthostereoscopic 3D presentation, you have a decoupling of these 2 cues, and this constantly puts a stress on your visual system, and that if you do it too long and too much, and with too much distance from the screen, it will create these bad effects from 3D, like motion sickness or that we have heard before. So you can translate that also into kind of production rules for stereoscopic 3D. And stereoscopic filmmakers know these very well. So you have a very limited depth volume, a depth budget where you can let your stereoscopic presentation be. So if you are close to the screen in these white areas, yeah, this accommodation divergence conflict will not be too big. Now, if you have constantly things coming out of the screen, like these popping out effects, things are constantly coming towards you, you have a bigger accommodation convergence conflict. And if you do that too much and too often, you will overstress the audience. Doesn't mean that you can't do it. So also in Disney movies, you will see some type of these 3D effects, but then the filmmakers really consciously decide, here I want to have a strong moment, I want to have a lot of depth, and I want to use it for my storytelling, but not to exaggerate all the time and have it too much. So that converts into such rules for stereoscopic filmmaking. And the problem in this is now our 3D world, you see it's kilometers and 2 centimeters that we can perceive. All of that can be in our brain. But this volume that we have here around the screen is very limited. So the question is, how do I do this mapping of the real world into this limited volume, still being aesthetically pleasing, still being transporting some artistic intent that you want to have with that, and not overstressing the audience and not making you vomit in the end of the movie. So that's what stereoscopic filmmaking means. So an example of something bad, so in this here, taken with a consumer photograph, she is just too close to the screen. It creates too much parallax, and the overall volume of the scene is too big. And here's something I will show you later, where we pushed her back in 3D space. Now you see she is further away now in this volume and having a more pleasant stereoscopic volume. Another, I will show you later that this gets the requirement of mapping the stereoscopic space once you have captured something. We will look at these examples. So you want to have expanding or compressing stereoscopic space as an editing tool on stereoscopic images and video. Another thing that can go seriously wrong is if now you have here this car is coming out of the screen and at the same time is being covered here by the screen. And that's something that in reality cannot be. So something which is in front of the window cannot be covered by the window. So our brain doesn't have a concept to resolve this area here perceptually, a stereoscopic window violation. So and what we did here is we detected this car is coming out of the screen, it collides with the border. I better push it back into the screen to resolve this stereoscopic window violation. And these stereoscopic window violations, they are also reflected by these areas here. So where something that is outside of the screen is colliding with the image border. So that's why this stereoscopic comfort zone is kind of converging towards you, towards the theater space. And here an example how conscious filmmakers do these decisions of design of their 3D sceneries. So this is, Disney has this archive of the legacy movies, and Lion King was one of the very successful ones, maybe the best one ever. So there is an economic interest in bringing them back to the movies, and one argument to do it is to do a 2D to 3D conversion. So we had this 2D movie and we converted it into a 3D version, and that was in the cinemas recently. And it kind of, to tell you the numbers, it was like 10 million roughly cost to make the conversion, and it was like 100 million box office revenue, so it paid off. So there is some very strong interest in doing this type of conversions. So now you have this 2D scene and you have to give it volume, you have to give it depth that is faithful to the original artistic intent, that gives it volume that should look natural. And here's what we did. So the chief stereographer, Robert Newman, he draw like disparity values in here. So he says like this should be +8 pixels disparity out of the screen. That should be like -20 behind of the screen. So he gives like a depth volume to the scenery. And this was then sent back to artists who were then literally drawing such depth maps and creating for every single image of the movie such depth maps, which would then allow you to create a second eye to your view. But this shows you how conscious they think of this volume and how a scene converts into that volume. And also, here you see something like disparity histogram over time. So a live action movie, we measured the disparity distribution here, and here is the frame number. And you see this is going synchronized with the video. You see like a histogram of disparities. And you see this scene is relatively shallow, and now we have a scene where something, now this thing is far out of the screen, and now it's like going back into the screen. And here it's coming back out. You see this, and also this one is coming out. So this tells you, shot by shot, the disparity distribution over time. And you see also that often in this scene, the thing is first in, and then it comes slowly out. So that's also something that our eyes need to adjust to the volume, as I said before. So first you give it a reasonably shallow scene, and then you develop this depth effect. Because if you would directly cut to it, close to it, you would overstress the audience. So often you see things that are slowly coming out or slowly going in. And all of these decisions of how to design the depth budgets are very, very conscious and design decisions in filmmaking. You see also there are scenes that are very shallow. Now you see here is a lot of depth of field. There's only this thing, and it has a very small depth volume. So here it is coming also out of the screen. And many of the scenes are, especially kind of dialogues, are more flat, and other scenes are getting more depth budget. And also this is, a good filmmaker will then use that as a means for storytelling. Now if you have a shallow moment, it shall give you this one, for instance. This one is very flat. Or this is very flat. You can transport some meaning with these things. So the depth budget of every single picture and also the transition over time is something that people are taking very conscious care of. And specifically also the transitions from a shot to another shot is something that someone really goes into and does a stereo depth grading in the end. So what you don't want to have is something where the audience focuses in front of the screen and then directly cut into something back of the screen, because your visual system just can't handle such fast changes. So on the other hand, the stereo filming means you have to have two cameras that capture your scenery and that then capture these two images that are displayed on the scene. And this is something that is actually extremely difficult. And because, for instance, if you capture a landscape scene and you want to put it into this volume, you have to put your cameras 20 centimeters away. If you have a dialogue scene where you have two actors talking to each other and you want to put it there, you maybe want to go even down to 2 centimeters camera separation. So meaning that this function of mapping the real world into the volume is given by the interaxial distance of your cameras. And it's by no means the eye distance that you have your cameras, but it's something that relates your volume to where you want to put it. So this requires a lot of knowledge about these mappings, highly skilled operators that choose these settings of interaxial and convergence, and you need highly complex camera systems that would allow you with motors to move the cameras to where you want and to converge them. So very expensive equipment, like $200,000, one of these stereo camera systems, and highly skilled operators. So in the end, all of this is a very difficult thing. So for us as researchers, it was a target. So can we do something which would make the thing easier, which would take as much as possible from this thing and put it into a computational system that would partially be automatic and do these operations. So the situation is here, you have all these very unintuitive knobs where you turn things and then that control this mapping into the 3D space. And we wanted to have something that is automatic as far as possible and that would also be intuitive, such that via intuitive high-level metaphors you would be able to control the system. So for instance, you would say, I want this in the zero parallax plane. So now you need a skilled operator that would turn the knobs of the camera to put it in this way. But if your system could measure where the parallax plane is and automatically control your cameras, you could just do the high-level design decision, the artistic decision, parallax here, and it would operate them automatically. So what we did is a computational stereo camera system that would operate with any rig. It would capture the stereo views, it would do a real-time depth estimation, and then you could control some of these high-level things via a multi-touch interface, and the cameras would execute this thing. So here is the illustration, demo of the system. We have this multi-touch interface. Now he is selecting focus and convergence. So he's saying, I want the system to converge and focus on this point. And as we have real-time depth estimation, the camera knows how to do this. So as he touches, you see it converges and focuses onto the desired things. Here we have something like tracking that also illustrates the capabilities. Now we say we want this in focus and convergence, and now as he comes closer, looking at the teddy bear, you see that it really follows him. It keeps him in a zero parallax plane. Showing that really the feedback loop from real-time depth estimation to automatic controlling of the cameras works. Also here we have something where you have your depth budget, you have the camera set for a scene like this, and then suddenly something gets into the screen which is too far. He comes too far to the screen, too much parallax, and here also, and now the camera measures that and changes the interaxial distance, makes it more pleasing, and now it relaxes back to the other things. So you can compute depth ranges and operating things, and the system would automatically execute those. Now this was again the tracking example. Now here also, by a touch interface, you can say converge and focus on him, and then it converges and focuses on him. And these examples, everything that you see is available online. With these publications, we have these videos in stereo, so you can look at how well it works. And yes, one part of the system is just the analysis thing. So that's also another thing that we kind of had as a product. So you just take the stereoscopic images and you give a visualization, a stereoscopic analyzer that would give you a histogram of your current depth. And it would also illustrate it on the video that is captured, and then the operator, so just doing the real-time depth estimation and analysis and displays it as a visualizer, and then the operator still has to do the changes himself. But it can also do, I talked about these misalignments that the cameras can have, if they are not perfectly set in parallel, you will have vertical disparities, you will also have rotating, keystoning, and all of that has to be taken care of. You want to get rid of that. And we have a system that measures automatically parameters, so how much vertical disparity, how much keystoning, and it can correct them, in this case, only by image processing. So it takes the video, the non-correct stereo video, and it gives out the corrected video. Yeah, another example, stereo 2D to 3D conversion, and very, a big thing. So many of the movies that you see in the cinemas are actually not captured in stereo, but converted. And it's a very difficult process where you have your 2D views and you first have to segment out all the objects from your video to separate them into different things. Then you have to recreate the 3D structure of the scene. And finally, when you have a full 3D model of the scene, you can do a view synthesis and to generate a second view for your first view. So that's a process that is done a lot. So Titanic is coming out. Old movies are being converted. Disney movies are being converted. Little Mermaid is currently being done. But also a lot of, as I said, movies that come to the cinemas in 3D are actually converted from the 2D version in such a process. And these are all difficult steps if you think you have to do that on every frame of a full movie. They are very disconnected. So there's someone spending hours on rotoscoping it, then someone else creates a geometry, and finally, after maybe a week's done by different people on different continents, so usually this manual work is done somewhere in India or in China on low labor countries. So it's a very disconnected workflow, and it's very expensive. So it sums up like $100,000 per minute that it costs to do this manual process. So again, for us, an idea, can we do something better? And we wanted to have something that would give you instant feedback. So as you do something, you see the result of it, and you operate with your 2D image until you're satisfied with the 3D image. So instant feedback, and we also wanted to have an intuitive interface. So this is what we came up with and what we call stereo brush. So you have your 2D image, and now you draw sparse scribbles onto this image. So these are now indicating the disparity, the distance in depth space. And you see I have like brushes. I brush onto these objects in the scenery. I don't have to accurately segment them out. And the system automatically computes a stereoscopic pair to that. And here you see an illustration of the disparity that is generated. And now I continue giving these sparse scribbles to the scenery until I'm satisfied with my depth volume of the scene. And you see in a few minutes I got a reasonably well designed stereoscopic representation of a 2D image. In order to do that, there is a process running behind that is transparent to the user. So he has his interface and he draws scribbles. These scribbles are diffused with a bilateral filtering approach to like what we call a disparity guess. We also estimate like important structures in the scene, and we also estimate edges. So there's a lot of highly sufficient image processing going in here. And finally, it creates a warping function. So it takes your input image and it warps it to a position where your second eye would be. And all this interaction that you do here happens in the image domain. So you're brushing strokes on images. That's why we call the thing stereo brush. So there's no real relation to a 3D model or so, which is unintuitive in that sense. And also the user can interact with any of these other masks that are generated. Yeah, another example. You see interacting with this depth map or with these depth scribbles, changes the depth layout of the screen. We also have like gradient strokes to adjust such gradients. And it's maybe not yet useful for highest quality cinema pictures, but at least it is very well suited as a very fast depth layouting tool that the artists can use to generate and design their desired depth distributions. So you see very few strokes can generate nice stereoscopic results. And you can also convert things that are actually do not convey a physical structure, like artist paintings, that you cannot necessarily take an artist image, convert it into a 3D model and re-render it, as it just doesn't obey the laws of physics. But with this approach, you can also do such things, which is, of course, important if you deal with Disney movies from the 40s or so. No? And if you do it for video, this is something we actually didn't develop too far. You have to do it on a few keyframes and then propagate this information over time. Also this disparity visualization is something that is actually very interesting for stereo production and the movie plane. So one thing how we often work with our business units is that we develop these tools, we do the research, we have a MATLAB or C crappy implementation that's just working to do the paper submission, and of course first we do a patent, then a paper. Then we have the deadline, and then some of the business units, hey, this is cool, can we have that? And then we have the problem to turn this research code into something that it's professional production software. But for that, we have a software engineering group that closes kind of this technology gap. And one thing that works very well with the studios to integrate plugins into their common production workflows. So Nuke is, for instance, something from the Foundry a stereo compositing tool that they use for film production. And yeah, we, for instance, provided such a tool for disparity visualization and manipulation, and they use that for stereo grading of the movies. Yeah, another thing, in the moment where you have a volume, also compositing and mixing and graphics overlay becomes, you have to rethink that, and I think there will be a poster tomorrow about things like that. No? So if you have something floating out of the screen and you want to put a graphics there, you have to make sure that you don't put it in depth behind it if you cover the pixels, as then you create a conflict. No? So often in the old days you have seen that, for instance, subtitles in 3D movies were floating very far out of the screen. No? But if you have an understanding of your depth volume, you can place them just as far out as you need. No? So by combining scene analysis, depth estimation with the subtitle placing, you can do a better job on this. Now, as you don't want to have these subtitles annoyingly far out of the screen all the time, as we have heard, that's something that really stresses the audience. No? So specifically in Switzerland, where most of the movies are in English, but we have French and German subtitles, so you have 2 lines of subtitles that are constantly floating here, the German and the French one, and they are completely distracting you from the movie, because the action takes place somewhere in the back, and you are constantly doing this. And we said this is one of the bad effects of 3D. So placing subtitles and overlays is a serious thing, and if you can measure the depth of the scene, you can adjust the placement. So here, for instance, we measured the depth of the scene, and each of these 3D logos is just at the right distance to the object. Also in 3D television, they had to make sure that they don't collide with the content, so all these graphics is flying out really far out of the screen, which is annoying. And also if you have if you want to combine stereo from different sources, you also have to think of the depth structure, so you have to have depth descriptions for instance, here we have this graphics element and the real scene, and if you, the compositing has to take into account also these depth relations. A few more examples. Yes, and then something which wants to answer the question, now if I have something captured, and I have a stereo scene at this onset, you can choose the interaction and distance, and then it's baked into the images that you have captured. So this was asking, can I do something after capture? Can I change the disparity of a stereo pair after the capture? Now, so let's think of this. Here you see this happy Swiss cow, and it has a certain depth volume, so the nose tip of the cow is coming out of the screen, and all the background is somewhere in the scene, so it has a certain volume. And here, you see we changed the depth description, so we pushed the nose of the cow back into the screen, so we did something like this operation, but we didn't change the background. So it's nonlinear in the depth space, in the depth range, a nonlinear depth mapping operation. If you look at the disparity histogram, and that was the input disparity, we kind of pushed everything back into the screen. And the way we did it is we've found a warping function, not taking my stereoscopic images and then pushing the content in a content adaptive and nonlinear way together, such that it would change the depth perception. So if you have, for instance, in the left and the right view the nodes of the cow, and you push them closer together, the effect will be that it will be pushed backwards in your stereoscopic image. So now the question is, how do I find this warping function that would do this desired change of my depth mapping? So first of all, let's define these mapping functions, and you can think of a linear function. So this is your input disparity, and I define something that changes, that halves my depth volume, so all the disparities are divided by 2, and I push it closer together. But you see that with that also I create something which we call cardboarding, so the volume of all the objects is also decreased, they get more flat. You can also define other desired functions. Now, for instance, you have salient objects in your scene and you want to keep their volume, but there is empty space in between, so you want to do something like pushing things forward or backward. And, well, you can define that as a nonlinear disparity mapping function. Now that would compress the empty space, but keep the volume of your salient objects unchanged. No? So this would be a nonlinear mapping of such a function. So that's my desired things that I want to achieve. And I do that via image warping. So I have here my input stereo pairs, and I have a pixel grid of these pairs. And now I'm trying to find a squeezing and stretching of the images that would implement my phi function. So I want to know how much do I have to squeeze this image in order that it has this desired depth change. And this can be formulated via some mathematical formulation as an energy minimization, and the solution of this would be this warping function. So I also do analysis of the images. So here you see disparities that we estimate. So we don't use dense disparity maps, as they are very difficult to get and erroneous, but such sparse disparities that we can get with a very high reliability and accuracy. And now these are the disparities, and I want to change them in a certain way. And that can be formulated. I'll go quickly over this probably. So each of these disparities shall change by a certain length given by a phi function. So if I have a disparity like this and I want to compress my scene, I want to make it smaller. If I want to expand my scene, I have to make the disparity bigger. And also, I counteract that by saying I don't want my image to deform too much. And especially, I have regions in the image that are important, that are salients, that are measured by such a saliency estimation. And then I don't want the changes of those salient regions to be too big. So it kind of counter affects my deformation. And that goes into this energy minimization, and the solution of this is such a warping function that now does something like this. So if you look at, this is the input, this is the output, and what it did, it stretched here the background where it is less visible, and it squeezed the background here and pushed the statue to the right. And you see, it didn't use dense disparities, which is impossible to get, no camera calibration, and it also doesn't create holes, so no inpainting. So what you can do with that now is you can virtually move your camera around. So you see it here. In a limited range around your input camera, you can create virtual camera views. But you cannot go very far away, as then you would expect disocclusions happening on your objects. So certainly you cannot. This very simple approach, if you want, is limited to a small change of your ranges. But now if you do this with both cameras, you can virtually, in post-production, change your interaxial distance, and with that you can vary the depth impression of the scene. And you can also do that locally. So here we don't change the background, as for instance here, this was too close to the camera, and we wanted to correct that by pushing this back. But we didn't want to change the scenery in the background. So we only operate on a locally adaptive, nonlinear way. So this thing that you see here is doing practically something like that. So this is a very basic algorithm that opens a variety of applications. So we can correct for errors automatically even, so that can run in a box after the camera system. You can, in post-production, correct errors. But it also gives you completely new art directability, so you can change the depth composition of your scene in post-production after shooting. And also, display adaptation is important, as it is in stereo audio, your 3D perception onto a 3D screen, you can try it out later maybe, depends on your viewing position. So if you move around, you see distortions. If you go further away, you also see some distortion. Meaning that something that was produced for a cinema screen will look different on a TV screen or on a mobile device. So you want to do a display adaptation, which means a virtual change of the interaxial distance, which you cannot do. But these algorithms here would allow to do such kind of a display adaptation. So that is shown here. That is an input, and that is automatically computed, doubling the disparity, which you would do, for instance, when you take something from cinema screen to an HD or lower resolution. And as it works automatically, you can even have like a depth button on your remote control that would allow you to adjust your depth impression to your needs. As I've shown you this problem before, we have the framing problem. The car is out of the screen, it collides with the screen. So we have this framing problem. So here we detected there is this window violation, and we push the car back with the same approach, and can, as an example of an automatic stereo correction. Another thing, of course, I can do virtual view synthesis, and that's something that is useful for stereo to multi-view conversion. So these autostereoscopic displays that are expected to come, they actually show more than 2 views. They show 9, 16, or even more views at the same time. And you don't need glasses to watch a stereo there. But the problem is content creation today is stereo, and it will remain like that. And also these autostereoscopic displays will have to work with Blu-ray players that have 2 views and TV channels that send 2 views. So we need something that would do an automatic view synthesis of these required views from your input views. So basically, you can use the same algorithm that I just described. It takes 2 input views, it does automatic analysis, it creates warping functions, and then can synthesize any view in between and also extrapolate to some extent. So you have a data extractor, the warp calculator, and then practically the n-view synthesis out of that. And this also illustrates a bit how these algorithms work in total. So this is your input disparities, showing you now the depth distribution, and these are those that you want to change. But you don't want to change the salient region, so these should be as untouched as possible. So if you squeeze and scratch, you want to hide that in the regions where it's less visible. So that's image saliency estimation. So now I'm imposing my phi function. I want, for instance, to divide or make it more shallow by 2, so meaning that all of my disparities are divided by 2. And this is where all these disparities then should move. And now imagine that these are control points that move a mesh that you have imposed onto your image, and now as these points move, the whole image will move to that position that you want. So that image domain warping by sparse grid points will do that. And we've shown that with this you can, in an automatic way, do very nice view interpolation that then enables you this stereo to multi-view conversion. So these are virtual views. So the first and the last are the original camera views, and everything in between is synthesized by this algorithm. And it works automatically, and in subjective tests also done in MBAC, we have shown that this works equally well, if not better, compared to methods that use depth maps, which are hand-tuned and optimized over years. So this approach of image domain warping, you've seen now this. In a transmission scenario, you would transmit only the views, and then all of this processing would be done at your receiver in the set-top box or the television, and it would automatically create these data. But you could also think to move some of that to the sender. So these are the calculation of the warps can actually be done already at the sender. So here we sort of doing that here and sending additional information in form of these warps to a receiver. And that's something, if you now look at these warp sequences, they are actually very regular. So if you are familiar with compression, that has a very low information content. You can compress these warps very, very well. And in experiments, we've shown that the overhead that you create is very small, very negligible, in addition to the video sending these warps, and you get this functionality of virtual view interpolation and support of autostereoscopic displays. So that's why also this extension of MPEG now currently working at the 3D extension of HEVC to enable autostereoscopic display support considers that as an ACI message to be included there. And as it's all automatic, we even have a hardware. We have some students looking at chip implementation. There is an ASIC already for the view synthesis, and we are looking to build a complete stereo to multi-view system over this summer to show this. I'm completely running out of time, but this is something that you are maybe most interested in. So we also look at computational perception, so of perception of stereoscopic 3D. So starting from perception models, knowledge about 3D perception, we want to create computational approaches that would enable us to capture features of stereo 3D and value them with regard to quality or to annoyingness, and then to analyze scenes, but also to predict and correct some of these errors. Now, so basically, we have the perceptual models, we have stereo as input, and we extract different types of features like saliency, attention estimation, or depth estimation, or significant features. All of those are kind of the ingredients which we then use to solve specific quality tasks. And one thing that we looked at first was detecting stereoscopic window violations. No? And the hypothesis, yeah, this is an illustration of that. Now, if this object is out of the screen, but it's partly covered by the screen, so you don't see this part, it creates the stereoscopic window violation. And you see they are hard to avoid, so it's really a problem for filmmaking as this space here in front of the screen gets really, really small. So it would be nice to use more of the screen and not having to avoid always these collisions with the borders. Let's keep this. And so the hypothesis that we also have as stereo perception depends on the frequency that you have in your content. It might not be the case that something like this, so this is colliding with the screen coming out of the screen, but it doesn't have a spatial structure. It is a window violation, but it might not be annoying. Whereas this one, where you have a lot of structure, your eyes can fuse it, this might be an annoying stereoscopic window violation. So we want to find out, can I get away with some of this, and where is the point where it gets annoying and I have to really start off thinking of correcting that? Because a typical thing is over-the-shoulder shots. So you have these over-the-shoulder shots. Often you have something which is blurred out of the screen, and you should focus on something inside the screen. So this is a typical over-the-shoulder shot, if you want. So and that's something that filmmakers like, and often they have the 2D version of the film where they want an over-the-shoulder, and in the 3D version of the film, you tell them, well, you can't do it because it's a window violation. They will hate you, the stereographer. So if we could tell them, well, you can do it, but you have to blur it to some amount in order to have the stereoscopic window violation not be annoying. So that was the motivation of this research. So we have to detect window violations, do image processing. We have made a subjective study to measure the annoyingness of different window violations, and then we came up with a way to predict how much annoying a window violation is. So these are different steps of this stereo pipeline. You see that there are kind of predictions, detections of window violations. And we did this a study where we varied the relevant parameters independently and came up with such annoyingness functions. So the more up this is here, the more annoying. This is the contrast versus frequency, so a CSF function, if you want, for stereoscopic window violations. And we came up with a model that could predict how annoying a window violation is. And yeah, we also validated this by another user study where people had to mark what they find annoying and what they don't find annoying, and then we matched that to our model predictions and had a machine learning algorithm that would adjust the two and came up with something that could reasonably well predict how annoying a stereoscopic window violation is. Well, I ran completely out of time, but I want to show you one more thing, which is a premiere. So you are the first ones who would see that, and it's really in your field. So this is something that will be published soon in the Transactions of Visualization and Computer Graphics, and it tries to go beyond quality. It tries to get the meaning of aesthetics. So can I capture the aesthetics of a photographic image? So the idea is you have bunches, millions of images, and is there a way to classify them into something which is clearly good images, which are clearly bad images like that one, and some that are kind of borderline. So we thought of, can we do such an automatic aesthetic evaluation of images? The motivation is clear. There are images, so that's from the parks. So that's clearly a good image that you can sell to a customer. This is not a good image. And they are good and bad in many ways. There are some that are semantic, but there are some that are also signal-driven. So for instance, the color is different, the contrast is different, and there are maybe things that we can use to classify something like that. So why do we consider this a better image than that one? In order to do so, we first need a conceptual framework. We need to understand aesthetics of an image on a conceptual basis, and then we will be able to create a computational system that might measure those. So that's something that we captured. And the main idea that we have here to come up with something we call aesthetic signatures. So we know image quality is a difficult task, and image aesthetics even more. But their knowledge, so other people approach that maybe from the machine learning side. So you have a database of images, you have people labeling what is good or bad, and then you have a bunch of criteria, and you match the two, and your machine learning algorithm spits out what you want. But we wanted to have a more high-level approach, so taking knowledge from professional photography, terms that people use to create good images, and to try to come up, in that case, with a 5-dimensional measure. So we identified sharpness, lens blur, colorfulness, tone clarity as dimensions that play into image aesthetics. And for instance, this one, it's out of focus, it doesn't have a good sharpness, so obviously it gets a low rating in sharpness, whereas this one has a high score in most of them. So all together, we predict that this is a nicer image than this one, and we also can use these different elements of our aesthetic signature still. And it's inspired from photography and should take the human visual system into account. And so what we did is that we did, again, a user study. So we presented images to people, and we asked them to rate the different levels of how good, how colorful, how sharp, how something is. So we had this ground truth of their image aesthetics, pleasingness from users here in blue, and we came up with computer vision algorithms that would be able to capture these categories. And then we tuned the two against each other, and we are able to get a pretty good estimate of this notion of image aesthetics that we got here. So we can predict how nice an image is. So for instance, if you see here, colorfulness is something that is maybe not always necessary. Such a black and white photo can also be very pleasing. But we have identified that sharpness is something that is really always necessary. So if you have a blurry image, there's no way to consider it would look good. So that could be also a tool to classify images, to select images, to tag images by their aesthetic pleasing, but it could also be used in Photoshop for giving you a hint on what you do for photo editing. So for instance, this image was converted here into this image. So there's some stretch, there's some change in color and sharpness, but all of these knobs that you have in Photoshop are very unintuitive. So you change sharpness, you change color, but it affects all these dimensions of image aesthetics. So this tool would give you, for instance, now, that was your input, and now these operations that you did turned it into that one. So this multidimensional thing could get a kind of rating of your image editing. And well, here's an example of these different categories that we have and how we measure them. But just let me close with this one, giving you a few more examples. So that's values of these things for that, the aesthetic score for this image. Or here you have this image and a certain aesthetic score, and then you do some image editing and you turn it into this aesthetic score. This is your input image, and that's your editing. You get some change in your aesthetic score. Or it could also tell you that these are examples of these knobs that you have in Photoshop. And if you play with them, it would tell you, well, you shouldn't do this edit because it affects your image in a negative way. So you could guide the user's editing by having such an aesthetic score. Yes, and with that, I think I thank you finally very much for your attention. And yes, if you have questions, and still is time.